calorimetry. Calorimetry is the measurement of heat flow. Okay, these measurements are made using an apparatus called a calorimeter, and a calorimeter looks something like this. Okay, where you have some water, you have a thermometer, and you have a reaction that takes place, and you measure the amount of heat through using the thermometer, and that way you can tell how much heat is released or flowed into the system. Some more vocabulary words. Heat capacity. A heat capacity is the amount of heat it takes to change an object's temperature by exactly 1 degree. So therefore, a calorie is a quantity of heat that raises the temperature of 1 gram of pure water by 1 degree Celsius. A big calorie, like I was explained before, is also called a dietary calorie. Always refers to food, and this is equivalent to 1,000 little calories. And a joule, which is the SI unit for heat and energy, 1 joule will raise the temperature of 1 gram of pure water by 0.239 degrees Celsius. Obviously, as you can see here, taking a look at a joule versus a calorie will raise the temperature up to 1 degree. This one will raise it up about 0.2 or 0.239 degrees, which is a lot less. So therefore, the amount of energy that you get out of a joule is a lot less than a calorie. And here's your conversion, where you have 1 calorie is equal to 4.18 joules. Or 1 joule equals 0.239 calories. Specific heat. Specific heat is the amount of heat it takes to change 1 gram of a substance by 1 degree Celsius. Specific heat capacity has 3 units. It has either an energy unit, it can be either in calories or joules. It could also be in kilojoules or kcals. Okay, we can just convert between those. But we also have grams per degree Celsius. Okay, so in other words, how much energy is required to raise a gram by 1 degree Celsius? The value of specific heat is different for various types of matter. Water has the highest specific heat, and the heat that affects the temperature of those things with high specific heats are much less than those with low specific heats. So for example, you understand that boiling water, it takes a long time to boil water. The reason being is because it has a high specific heat. Okay? And it also is absorbing a lot of water. So once you heat up that water, it will cool off for a long time. Whereas if you take a piece of metal and you heat it up, it heats up almost instantaneously, which means it doesn't take a lot of energy to heat it up, which therefore means it has a low specific heat value. Okay? Which is the reason why they make ovens and toasters and things out of metal, because they don't take a lot of energy to heat it up. Here's an example of a table, and you can see here that we have specific heat, which is the amount of energy needed to raise 1 gram by 1 degree Celsius in joules. We also have molar heat capacity, which is the amount of energy to raise 1 mole of a substance by 1 degree Celsius. Okay? As you can see here down at the bottom, water has a very high specific heat, which means it takes a very long time to heat up, and a lot of energy is inputted in order to heat up that water. Whereas aluminum and copper, so on and so forth, gold, iron, all these metals, like I mentioned before, do not take a lot of energy to heat up, which is why we make a lot of parts that we need to heat up very quickly out of metal. Calculating heat energy, well, here's this equation. You have Q equals Cm delta T. So heat equals specific heat times the mass times the change in temperature. Okay, so C equals specific heat. Mass refers to M, and change in temperature refers to this delta T. Okay. So again, specific heat is the amount of heat required to raise 1 gram of substance by 1 degree Celsius. Mass is the amount of mass of matter being measured, and we always measure mass in grams. And change in temperature is the increase or decrease of temperature of that matter, and we use T final minus T initial. Okay? T final minus T initial is equated to delta T. In summary, in a system, we basically, or if you're dealing with substances that are connected, like a surroundings and a system, whatever is gained by a system or surroundings is also lost by the system or surroundings. So for example, if you take a hot cup of coffee, okay, and you put it out in room temperature, well, what happens? What happens is that temperature of the coffee is probably going to decrease, right? Because the surroundings is a lot lower in temperature. But what's happening to the temperature of the surroundings? Well, it's also increasing. So whatever is being lost by that cup of coffee, whatever heat is being lost by that hot thing, is also being gained by the other. Okay? And we can denote that equation as this. Okay? Where the thing gaining, where it has a specific heat, it has a mass, it has a change in temperature, is also being lost by the other when they're connected. So you have specific heat of that thing times the mass times the delta T of that thing. But notice the negative, which means that the energy is being lost. Okay? So this picture is just saying, so if this was a hot cup of coffee, well, what's happening is that the heat is escaping and going into the surroundings, okay? And what's happening to the temperature of the coffee? Well, the coffee is dropping. At what point will it stop decreasing in temperature? Well, when the point of equilibrium, when the surroundings and the system are at the same temperature, that's when everything stops and everything's at equilibrium. So here's an example of the sample problem. So it says the temperature of a piece of copper with a mass of 94.4 grams changes from 25 degrees Celsius to 48 degrees Celsius when the metal absorbs 849 joules of heat. What is the specific heat of copper? Well, we know that the basic formula is Q equals MC delta T. Okay? In order to figure out for specific heat, you have to do some algebra in order to solve for that little letter C. Once you have C, you can fill in all the other numbers to solve for the problem. Okay? So when I do that, I get C equals Q divided by M times delta T, and I plug in my numbers, and I get this as my answer. Okay? So if you follow these 3 steps, you give the basic formula, you do the algebra to solve for whatever variable it asks you to do. In this case, it's specific heats. We know we're going to be solving for C. Okay? And then you fill in the numbers accordingly and solve for the problem. You're going to be fine. Here's another sample problem. What is the specific heat of a substance that absorbs 2.5 times 10 to the third joules of heat when a sample of 1.0 times 10 to the third grams of the substance increases the temperature from 10 to 70? Again, we start off with the basic formula. We manipulate the formula to solve for the variable that we want. In this case, it's specific heat again. We plug in the numbers and we solve, and we get that as our answer.